Alright, so it's been a while since I've made a video, but I've got this new idea to make solutions on the 2024 Step 2 paper. Not sure about Step 3 yet because I don't know how much time I'll have, but if I do have time, then I might make solutions on Step 3. That probably won't be the case though. Uh, anyway, I'm making solutions on this because this is actually the paper that I sat. So I did this paper. I didn't do that well in it, which is why I decided, I got to get my revenge on this paper and make solutions on all of the questions. So the idea is there's 12 questions here, so I'm gonna have 12 videos on each of the questions, and this is question one. So if you want to try this question, this is the full thing here. Um, and I didn't actually do this question when I did uh the step paper, but I probably should have because this is honestly not too bad compared to the other questions. Um, anyway, let's just get into the first part. So they tell us this, they give us this equality, right? Which it's basically just an example of what they describe in the first part of the question, which is good because when you're given an example, it helps you understand a bit more about what is going on, and it helps like remove any misunderstandings, I guess, or helps clarify things. Importantly, something to note is that n, k, and c are positive integers. Now, I don't actually know if that includes 0 or not. I don't know how Step likes to do things, but I don't know if that's... I don't think that's relevant in this question anyway. Um, yeah, so once you've like fully understood like what they're trying to say, uh, you say they ask us an if and only if thing, right? So we can either go from this equality to this statement, or we can go from this statement to the equality. And I think it's pretty obvious that it's better to go from the statement to the equality because that's it's just more intuitive that way. You can work with this statement easier than you can work with this equality, right? It's like not really clear how you can manipulate this equality. So let's just start with the statement first. So I started with the first part, which is the sum of the n plus k consecutive integers from c upwards. And I wrote that as like some kind of sequence. So we have n plus k times, we start at c, and then we end at c plus n plus k minus 1. And you can actually verify it's like this because they give us the example, right? So if you just plug in the values 4 for c and 5 for n plus k, you should see that this matches up with this left-hand side of the equality. And from here, you can think about it, or you can work in terms of sums, so like sigma notation, or you can work in terms of like what's it called, series, so like an arithmetic series where the common difference is 1. I worked with sums because I just thought that was easier for me, and that's what I thought of first. But you can do series, arithmetic series. That's probably also a bit easier, but I'm not sure. Anyway, once you turn it into sums, you get something like this, right? Where you start at I equals 0 because you want to include just c. And the idea is I wanted to use the sum of the first n consecutive integers, right? Which is equal to n times n plus 1 over 2. But the thing is, you need to start at I equals 1, right? So we need to get rid of the I equals 0 term, which we can just do by manually computing the I equals 0 term. So when I equals 0, you just get c, right? So then you can just put that outside, and same for the right hand side. Uh, and then from here, you can use the formula n times n plus 1 over 2. Oh yeah, also for the c case, because c is just a constant, right? And you're not changing anything in this. You're just adding c n plus k minus 1 times. So that's why you just multiply it by the upper bound. And once you do it for both sides and then simplify, it actually simplifies quite nicely. Like most things cancel out and you get actually what they want. So yeah, this one is not too bad. And you can probably actually argue here that because we've only used equality here, we can say that like each step is an if and only if step, right? So we don't actually need to go from this statement to, or this equality to the statement. We just say, oh, this is true if and only if this is true, if and only if this is true, and then so on until you get to the statement. Yeah, so let's move on to the next part. Find the set of possible values of n and the corresponding values of c in each of the cases where k equals 1 and k equals 2. Well, when we plug in k equals 1 in here, we get this, and we simplify it down to n squared is equal to c. So if we remind ourselves that n and c are positive integers, we can conclude from this that if c is equal to n squared, that c has to be a square number, right? And n can be any positive integer, right? Because if, let's say n equals 1, 1 squared is equal to 1, that's still a valid equality, because in that case, n and c are both positive integers, right? 1 squared is equal to 1. That works. N squared, if n is equal to 2, then that would still hold true. N squared is n is equal to 3, that would still hold true. So yeah, that's fine. But it doesn't work the other way around, right? So if c is equal to 3, that equality doesn't really work if n and c are both positive integers, right? Because c is equal to 3, then what can n be? n would have to be square root of 3, which is not a positive integer. So yeah, you have to conclude that n can be any positive integer and c has to be a square number, or the corresponding square number to n, because they talk about corresponding values of c. The next case is when k equals 2. Well, when you plug in k equals 2, you get this, right? And then you simplify it down to this. And what you have to notice is that this 2c plus 1, that's in the form of an odd number, right? And that's because c is a positive integer, right? So 2c plus 1 has to be an odd number. And we have that n squared is equal to an odd number, right? So if n squared is equal to an odd number, that means that n has to be an odd number as well. So we conclude from it that, yeah, n squared can be any odd number, hence n has to also be an odd number, right? Because an odd number times an odd number is equal to an odd number. If n was even, then n squared would be even. And then the corresponding value of c is when you just rearrange for c. And then the next part is show that there are no solutions for c and n if k is equal to 4. Well, again, just plug in k equals 4 into the thing, or into the equation, and then you get something like this. And then rearranging for n squared, you get something like this, right? And so whenever you get something like, oh, show that there are no solutions, the first thing that comes to mind to me is like a contradiction, right? So let's assume for the sake of contradiction that there are solutions for n and c, because you can't really solve this by like a counterexample, right? You can't counterexample every possible solution for c and n, right? So you have to go like solve the opposite way. You have to assume that there are solutions and then come to a contradiction. So when we assume this, maybe there's other ways, but this is the way that I thought of doing first. I minus by 4c, and then now we have two variables that equal to an integer, right? So we can factorize this using the difference of two squares, and then just consider the factors of 6, right? So we have either 6 times 1 and 3 times 2. Remembering that this remembering that n and c are both positive integers, right? So this factor has to be greater than this factor, right? So this has to be 6 and this has to be 1 because we know that this is greater than the other factor. And the other case is when we have 3 and 2, right? So if we just consider those two cases, you get something like this, right? And then solving for n, because that's easier than solving for c, you get 2n is equal to 7, which can't be true if n is an integer. And 2n is equal to 5, which is also a contradiction. Hence, there are no solutions for n and c. Maybe there's some other ways to like show that there's no solutions, but this is just the way I've thought of doing first. And if you do have any other solutions, please be sure to let me know. Because I mean, like, we're all here to learn. The next case, consider the case where c is equal to 1 and find two possible values of k and the corresponding values of n. When you do plug in c equals 1, you get something like this, which simplifies to this. And then I just solved for n squared, and I noticed that like it's the same as the formula for the first consecutive k integers, but to be honest, you don't really need to like mention that. I did use it to find the second pair for k and n, but to be honest, you can kind of like cheat and use the next part to find the other solution. Anyway, we'll just stick on this part for now. Yeah, they ask us to find values of k and n that basically satisfy this equation, right? So hopefully, I mean, the obvious solution is just plug in n equals 1 and k equals 1. And then to find the next solutions, I used this idea, right? So that n squared is equal to the sum of the first k consecutive integers. So I just went like, oh, 1, checked if that's a square number, which that's how I got the first solution. And then I added the next consecutive integer, so 1 plus 2, check if that's a square number, and then plus 3, check if that's a square number, plus 4, and so on. And then when you do that, you should find that when you get to k equals 8, so the first 8 consecutive integers from 1 upwards, you get that that's a square number, which equals 36. And so then if n squared is equal to 36, then n is equal to 6. And that's how you get the second solution. But to be honest, as long as you find this first solution, you can use this next part, which basically tells us like if you have a possible value of n and a possible value of k, you can find another value for k and n such that it satisfies this equation. So if you plug in k equals 1 here and n equals 1 here, you get another value of n which satisfies it, which you get 6 in that case, and k equals 8 when you plug in n equals 1 and k equals 1. So yeah, you could sort of cheat there, but this part basically tells you to show that this is true. So we basically just need to show that n prime and k prime are possible values for this equation. So we just need to show that basically this equality is true. So how do we show this equality is true? Well, the only information we're given about n prime and k prime are that they're equal to this. So let's just plug these values into here, like substitute them. And when you do that, you get something like this. And then when you expand that out, which it seems kind of long to expand out, but in terms of like step, this is actually not too bad. And a bunch of things cancel, which is nice. And then you get something like this, which we know is true, right? Because we're given a possible value big N of n. So we know that n, big N, and kn satisfy the equality, right? So we know that this is true. Yeah, we know it's true because we're told n and k are possible values. Hence, n prime and k prime are also possible values, right? Because we just went to equality, right? All of our steps were equality. So if this is true, then this is true, then this is true, and so then this statement is also true. Is also true. Yeah, so that's that part. And then the last part, oops, I sort of gave spoilers. Find two possible values of k and the corresponding values of n, or two further possible values of k. Well, we were given a recurrence formula, right, for finding like new values of n in k. So we just use our previous values, right? We can't use k equals 1 and n equals 1 because that gives you this pair, where k equals a and n equals 6. So let's just use this pair, k equals a and n equals 6. Plug that into here, and then you should get n is equal to 35 and k is equal to 49. And then you need to find another one, right? Because so far we only have 3, and they want 2 further possible values, so they want 4 solutions in total. So you plug these two back into the formula, and you get n is equal to 204 and k is equal to 288. And that's the whole problem. Oh yeah, I do also want to say, like, I have this section on afterword. So like, if we consider like what this question was actually trying to like tell us, right? Because step questions are always trying to teach us something, in my opinion. The last part was just talking about when c is equal to 1, right? So they talk about the sum of the sum of the n plus k consecutive integers from 1 upwards, right, is equal to the sum of the next n consecutive integers. So that would be something like this, right? So we have 1 plus 2 plus 3 up until n plus k, and that's equal to the next n consecutive integers. So something like this, right? So for example, k is equal to a and n is equal to 6, you get something like this, right? Which is kind of cool. But the question is basically giving us a formula for finding new values of n and k that satisfy this like property. And we're actually able to find greater values because because we only have like addition here, right? Like we know that this has to be increasing because we know n and k are positive integers. So the new values that we find, they're always going to be bigger than the previous ones, right? So we've basically shown in this question that we can find an infinite number of these solutions and infinitely large values of k and n that satisfy this property, which, I don't know, I thought that was just pretty cool. But yeah, that's the whole question. Thanks. Goodbye.